Let's do a quick review. First, we're going to look at this question here and create a box plot. Below is a distribution of the amount of water discharged to the Gulf of Mexico from 1954 to 2001 from the Mississippi River. The 5-number summary of data is as follows: 290, 444, 560. So again, this is in order. A truncated data set only containing a portion of the lower half of the data and the upper half of the data. Most of the middle values have been removed, appears below. So looks like we got to this point here, 430, there's 430. And then somehow it picks up later in 680 sometime. So yes, the big chunk of information is missing here, creating the rest of it. So we have kind of an end points. Calculate the upper and lower fence. So I'm going to use the information here, calculate the, I'm going to call it UF or upper fence. For the upper fence, I need Q right there, 670. Then I'm going to add and go 1.5 times the IQR, which is going to be 670 minus Q1, 445. So I do a quick calculation here. I'm going to get 1,000, so 1,007.5. Great, that's my upper fence. Okay, I can see immediately that for the upper part, there are no outliers. Since that's my upper fence, the maximum is 900, not above that. Let's calculate the lower fence. In fact, I'm going to calculate one more thing. I'm going to calculate the IQR. IQR is going to be 670 minus 445. I want to get a sense of the middle. Looks like it's 225. The middle, 95%. So from 670 to 445, somewhere in there, right? 450, but yep, somewhere in there. So this part, somewhere in there. I get 225. So the lower fence is going to be 445 minus 1.5. And then 225, the IQR. When I do that, I get 107.5. Okay, so now in the lower end, my lowest value is 290, which is well within the lower fence. So this one has no outliers. So we have no outliers for this data set, and I can see the IQR is pretty wide. That makes sense. In other words, this is, if that's the IQR, it is pretty wide, a lot of spread. It's going to take a lot for a value here to become an outlier. So use the information you have found to create a box plot underneath the histogram. All right, so I already kind of made my first marks here. That's about 4, maybe a little more accurate. Can I? Not really. 445, 670, a little, yeah, jeez, you can't. No, this is 600, 650, so 670 is actually somewhere over here. And then 560, so that's 550, 560, just somewhere there. So there is my box plot, but now there are no outliers, so I just need to find the maximum. 900, or 900 is the maximum, so I'm going to go right at 900. And the lower value is 290, so there's 200, 250, 290 is almost at 300, so somewhere right there. And there is your box plot. There's no outliers. That's all you get. Use the information you have to create a box plot. Yes, I did that. Boom. All right, so there you go. Let's go look at number 11 here. Again, just to point out that IQR has a wide spread. So therefore, like for example, some people might say, well, this value is apart from the rest, so this is an outlier. But the answer, but you can see immediately that's not the case. So just being apart means nothing. It has to do with how spread out this middle part is. How much variability does the middle 50% have? Because we're using that to judge everything else outside of this. Well, let's draw on a possible histogram that matches the shown box plot. I'm going to do this. I'm going to erase this. I'm going to go, this is 0.05. This is 10. So it means this is 0.15. It's 2. And it's going to be 0.25. And I want to draw a possible histogram that matches the shown box plot. Make the class width of the histogram 2 units wide. As the tick marks below are spread by that amount. So in other words, here's 60, 62, 64. So the tick mark here is 2 apart. So I'm ready to create my histogram. Between 60 and 64, I need to create rectangles. But the only thing I need to keep track of is the fact that I need to get 25% of the information. That's what this tells me. So I need to get 25% in there. So how do I do that? Well, what I really want you to understand is that there's many possible histograms. In fact, I'm going to do the same thing here. 0.15, this is 0.25. So one thing I could do is go, for example, let's say that this first part is 10%. That means now that I have to get 10% right here. So I need 50% to get to the total of 25%. So the next rectangle, that commits me to this. Now, when I get to the next quartile, that's it. This is 2 units wide. And I know this has to have 25%, so there's nothing more to think about. I need to raise this rectangle to the relative frequency. Again, this is a relative frequency. So n must rise to that amount. What about here? I mean, I could have done something entirely different. Maybe the first one is 5%. It should be 10% here, 5%. And then after that, if that's the case, then the next one must rise up to 20%. 5, 10, 15, 20. So that, I need that to happen. Now the next one again is locked in because it has to be 0.25, so I must rise that one to 0.25. So you notice you're not going to get the same rectangle. There's many histograms that can match this graph. As a matter of fact, I'm going to even change it up just to kind of point something out. It could have been this. Let's say I raise this one to 5, 10, 15 instead. So if I did that, then the next one can only be 10. So I need to go up to 25. So no, it looks different. What about here? Well, again, I have 3 units to go through, so I have a lot of choices. I just need to get up to 15%. So one thing that could happen is that this part is blank. Maybe I go up to 15% here. And if I do that, the next one has to be 10%, because 10% plus 15% gives me the required 0.25. Or I could do something like this. Maybe this is going to be, maybe this is kind of nice and smooth, and I'm going to go 5, 10, 15. And if I did that, I have 10% left to do something with. So maybe I'll go 5%, 5%, something like that. So in fact, I think I'm going to make this one a bimodal one, just to make the point. So let's say now I have the rest of this to do out. I need to have 15%, 25% for the rest here. And let's say that I'm going to go 5%, 5%, and it's at 5, 10. Can I do this? 5, 10, 15, 20. I sure can. 25. Again, there it ends. So 5, 10, 15, 20, 25. And these are 5 high. And there you go. There's that histogram. On this one, I'm going to do something entirely different. I'm going to say this one's blank, blank again. And maybe I'll go 5% here. And then, see, I have a lot of real estate here. What if I wanted to make this one a little larger at 15%? So what do I have? 5, 15, that's 20. I only have 5% more to deal with. So maybe I'll do this. Half of 5%, half of 5%, and there we go. So all these add up to 25%. Notice there's many histograms that can match this box plot. So the box plot just gives you no detail. It's not about quantity. This area is not about quantity. This is about spread, how spread the information is. But the histogram is about quantity. And that's why you see very different graphs being generated. I do not know the detail between these lines. All I know is that it encompasses 25%, but how the 25% is spread out within here, what does it look like? How is it distributed? I have no idea. I hope that helps to kind of understand the difference between a histogram and a box plot. Box plot is all about measuring spread or depicting spread. I guess you're not measuring, you're displaying. Should we go displaying? So this is about displaying spread, and this was about displaying the distribution. And if I looked at this and you asked me what most likely is the histogram shape that would match this, I would say left skew. Now, in this case, it's not. It's a bimodal thing, but I would know. So if you're asked in the homework to give me the most likely shape, well, the most likely shape of the histogram or the distribution is left skew. Here in this case, yeah, it is left skew.